Welcome to lecture 52 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on transformation electromagnetics for antenna applications and stealth technology. Here is the lecture outline. We will discuss about transformation electromagnetics for antenna applications by first introducing the topic and its theoretical background, focusing on the discrete coordinate transformation, and then we will take up some design of antennas based on the discrete coordinate transformation. We will discuss about flat parabolic reflectors and flat lens antenna. Then we will move on to the topic of metamaterials for stealth technology, where we will introduce stealth and metamaterials, and we will see how metamaterial structures can be used for stealth applications. So, let us first focus on transformation electromagnetics for antennas. So, currently the electromagnetic cloak designs primarily rely on metamaterials and transformation optics or transformation electromagnetics. Free space cloaks are basically challenging, as we have discussed earlier also. They are challenging to implement because they impose requirement on metamaterials that have got some extreme properties of permittivity and permeability. So, theoretically they are possible, but challenging to fabricate those kind of devices, right. So, transformation electromagnetics here will serve as a valuable design tool for antenna engineers that can also help in developing some novel antennas. Okay. So, other than cloaking, this transformation optics or transformation electromagnetics can also be used for beam steering devices such as antennas. So, you can focus or steer the radiation at a particular direction. You can also control the direction of the electromagnetic beams. So, some example antenna designs will include flat parabolic antennas and flat lens antennas, right. So, typically these designs require isotropic and exotic materials. So, here we will see that transformation electromagnetics will leverage the symmetry of electromagnetic fields, which is basically rooted in the form invariance of Maxwell's equation that undergoes coordinate transformation, right. So, transformation electromagnetics will basically provide precise control over the electromagnetic waves paths using these engineered materials, and it will mimic the coordinate transformation to guide wave trajectories. So, this approach provides innovative ways to manipulate electromagnetic space. So, in the traditional antenna design, which is a well established field, this is typically how it works. You have a transmitter, then a transmission line. This antenna portion is basically the transition region where it basically radiates out to free space waves. Okay, it propagates as plane waves, as you can see, and then again on the receiver antennas transition wave, this is coupled to the transmission line and received at this particular receiver circuit, right. So, engineers basically typically rely on years of experience to develop new configurations, right, and the ultimate goal is to basically meet the desired performance specifications, okay, better than the legacy designs. Now, you can introduce a new kind of antenna design concept by using transformation electromagnetics. How you can actually take help of Maxwell's equations, which are invariant when you transform from one coordinate system to another. This will basically help you to design material parameters of the medium in which an antenna is going to be embedded. So, the final aim here is to achieve desirable antenna performance, which is otherwise difficult with conventional approaches or medium. So, for that let us have some theoretical background. Okay. So, we understood that transformation electromagnetics evolved from early cloaking concepts which are basically used for materials that could bend or reroute light to electromagnetically conceal objects. Okay. So, they basically evolved from a concept of magic cloaks. So, what do you see that what is the methodology in this case? So, original electromagnetic field setup can be mapped into a Cartesian mesh, which is shown like this. Okay. Now, if you have a bump on a flat surface, okay, that should become flattened in the new coordinate system. So, the material behavior should be modified via this transformation equation that will help you to preserve the earlier wave behavior as if the bump does not even exist. Okay. So, the key result will be to see that light is basically traveling undistorted in this transformed system. So, you can overlay an inhomogeneous material blanket that can bend light around imperfection. So, here it is like you have a imperfection. So, you just bend the light around this imperfection and exit in the same way it was entering this system. The same thing you can also see here in the case of carpet cloak, where you have a flat ground plane, then you have some bump. So, because of this bump, the reflected wave would have scattered in different directions. But now, when you put a carpet cloak that conceals the bump in such a way that overall it gives you an effect of a flat ground plane, so that the reflected light goes as if there is nothing hidden. Okay. These concepts we have basically seen, but we will show you that how the similar concept can be also used here to make antennas with some specific functionalities. Right. So, discrete coordinate transformation is a practical form of transformational electromagnetics, which enables coordinate system transformations in a discretized format. Right. So, let us look into this discrete coordinate transformation and how it is implemented. So, here you can see the virtual space, okay, and the physical space. So, you have a parabolic reflector. Okay. So, let us implement this discrete coordinate transformation. Okay. So, here you can see both the virtual space and the physical space are discretized into small cells. So, what you have here is a parabolic reflector, as you can see. This is a PEC, and then this is the virtual space which has been now mapped into a physical space which is uniform, right, and flat. So, in both cases it is basically you have used quasi orthogonal local coordinate systems. Okay. So, this is a transformation of parabolic reflector in the virtual space. So, you can see this is the parabolic reflector that can be transformed into a flat one into the physical space. So, these are the new coordinate systems x prime and y prime. Right. So, what will be the definition of this coordinate transformation? So, the transformation between the virtual space, which has got local coordinates of x, y and z, and the physical space which has got the local coordinates of x prime, y prime and z prime, that can be defined like this, that x prime is basically a function of x, y, z, y prime will be also a function of y, x, y, z, and z prime is as a function of x, y, z again. So, you have to find out that what is the transformation. We have already seen that the transformation can be mapped onto the physical property of the material. So, you have to find out the new permittivity tensor that will actually absorb this coordinate transformation into it. So, you can obtain epsilon prime, which is the new permittivity tensor, that is given as j epsilon j transpose divided by determinant of j. Okay. Permeability tensor will also have the same form. Mu prime will be j mu j transpose divided by determinant of j. So, these are the new permittivity and permeability tensors in the physical space. Now what is J? You already remember from the previous lectures, we have seen that J is nothing but the Jacobian matrix. Epsilon and mu here are the original permittivity and permeability tensor. So J transpose is nothing but the transpose of the Jacobian matrix, and this is nothing but the determinant of the Jacobian matrix. So once you know the coordinate transformation, that is the relationship between the new axis and the old axis, you can calculate J, which is basically obtained as a matrix of the partial derivatives of the two coordinate systems. So dou x prime by dou x, dou x prime by dou y, dou x prime by dou z. X, y, z are the old system, x prime, y prime and z prime are the new system, right? So this is how you can calculate. I am not reading out all the parameters, you already know this. So what you can see that the initial material properties in the virtual space can be obtained for this kind of a parabolic reflector. So the original tensors were considered to be because it's a simple parabolic reflector, which is nothing but a curved PEC, okay, kept in free space. Okay, so the original tensors can be taken as epsilon equals epsilon naught I, and mu can be taken as mu naught I, where I is basically the identity matrix. Now in the transform system, epsilon prime and mu prime will be both position dependent tensors, and that means they vary with space, and these new values of permittivity and permeability will make the electromagnetic wave to behave as if the space is basically curved like this. Okay, so you can assume some scenarios like 3D volume of space in the Cartesian coordinate system, and then you can think of another second volume which is given by this distorted coordinate system, right, from where you can take 2D cut planes and they will basically look like this particular figure, right. So here the incident electromagnetic wave basically travel from point to point in both the coordinates. So the end-to-end propagation remains same, just that within the system their routes are different. So in the distorted coordinate, the wave is not going to reach to that gray object, and that is how it is basically skipping it, right. So what is happening? The space transformation is basically going into the material design, right. Here also these are the practical example that you already have a physical space with the object, so that distorts, so you can move it to the virtual space with like uniform grade. So this can be back and forth either way. This can be the physical space, this can be your virtual space, and so on, right. So all these things can be done by coordinate transformation, and you have to find these engineered materials that are basically helping you guide the electromagnetic waves in this distorted coordinate system following some curved paths. Now let us look into the design of antennas based on the discrete coordinate transformation. So let us look into the design of antennas based on the discrete coordinate transformation. So the first example we will be taking here is the design of flat parabolic reflectors. So parabolic reflector antennas are one of the most commonly used antennas across radio and optical frequencies. Their main function is to transform a spherical wave from its focal point into a plane wave, right. So the result is that it can generate highly directive beams, and one disadvantage is that the antenna size can be really large at low frequencies, and it could be challenging to construct due to its parabolic shape, right. So one may think of some all dielectric flat reflector, if that can be designed to replicate this parabolic reflector antenna's performance, but everything is done in a very compact volume. So there you can think of using this discrete coordinate functionality or discrete coordinate transformation functionality, that can flatten your structure while preserving the feature of the antenna, right. So this is how typically the parabolic reflector looks like. So based on the parabolic equation, you can write r theta equals 2f divided by cos theta, where r is basically the radial distance from the focus to the reflector surface at an angle theta, f is basically the focal length, theta is the angle from the central axis and aperture, right, that is basically the physical width across the reflector opening. Now this type of antenna can be designed to operate over a wide band of frequencies over C and X bands. Suppose if it is designed for C band, it will be working between 4 to 8 gigahertz, and if it is for X band, it will work between 8 to 12 gigahertz. And in such case, typically the focal length is around 108.6 millimeter. The angle theta is considered to be from minus 48 degree to 48 degree. That means the design is basically optimized to collect and radiate energy over 90 degree field of view, which is typical in reflector antennas. And the aperture is also 180 mm, which is the horizontal opening between the two edges of the parabola at plus minus 45 degree. Okay, so here is how the parabolic reflector geometry looks like, okay, with plus minus 45 degree aperture. So with these values you can obtain what should be r, that is 2 into f divided by 1 plus cos theta, that comes out to be 127 millimeter. Okay, so when you talk about C band, okay, which is again 4 to 8 gigahertz, and X band which is from 8 to 12 gigahertz. So they basically correspond to wavelengths of typically 75 millimeter, which is for 4 gigahertz, and on the upper hand it will be like 25 millimeter for the case of 12 gigahertz. So typically from 25 mm, so this is basically the lower bound for the wavelength, because this is the higher bound of the frequency. So typically from 25 mm to 75 mm, that is the lambda we are talking about. So you can see the aperture is basically spanning somewhere between 2.4 lambda to 7.2 lambda across the full band. That means the reflector is actually large, but it can provide good gain and directivity in the both bands. Okay, so what do we see, that with 180 mm aperture and 108.6 mm focal length, the antenna is able to provide high gain, moderate bandwidth and good directivity, but it is electrically large because it needs several lambdas to operate, right. So physically it's big, okay, in the sense. Okay, so here the objective would be to create a flat alternative to this parabolic reflector using discrete coordinate transformation. So one alternative to the parabolic reflector, okay, would be to flatten out the structure, as you can see here, okay, in using discrete coordinate transformation while preserving the functionality. So here you can see the actual antenna, right. So it is the parabolic antenna or parabolic reflector that is located in free space, okay, as you can see illustrated by a curved PEC. Okay, and this is the physical space with the Cartesian coordinates. So here the parabolic reflector is basically transformed into a flat PEC, right. So that is the difference in the two cases. This is the physical space we are going to design now. So what we are gaining out of it, we are able to make a flat all dielectric reflector that can replicate the parabolic performance. So the shape constraint can be reduced. So here are the implementation details. So a parabolic reflector designed for around 10 gigahertz can have aperture of around 180 mm. So transformation region in this particular figure is applied over 300 mm and 300 mm this way, from minus 150 to 150 and around 75 mm. So this is the overall space. So this quasi orthogonal grids that you see, they are basically generated using point wise software. They are basically applied in both virtual and the physical space, and that basically leads to the creation of an all dielectric flat reflector. So what we are worried now, we need to find out the permittivity distribution, okay, for this flat reflector. So using the equations that you have seen earlier, you can calculate n prime square, which will be nothing but epsilon z prime over epsilon naught, that is 1 over determinant of j, okay. So j is the Jacobian matrix for this transformation, which we have discussed earlier, and n prime square, okay, is also nothing but delta x delta y divided by delta x prime by delta y prime, okay. I think there is a typo, so it will be double prime, okay. So this n prime is basically the effective relative refractive index, and these are nothing but the delta x, delta y, delta x prime and delta y prime are nothing but the dimensions of the cells in these two particular spaces, in the virtual space and the physical space. From there also you can obtain this, right? Yeah, so this is n prime square. So next you have to map the permittivity, which is shown here in figure 4, okay, that is composed of 64 by 16 square blocks. So you can see the permittivity distribution, the color scale shows you the values of the permittivity that has been obtained, okay. So what you see here, this particular kind of simplification has applied to eliminate sub-unity permittivity values, which are very difficult to achieve. So here all these values are practically easy to achieve, okay, and you can approximate the structure using cluster of dielectrics, so that make it easy to fabricate, and it is also easily extendable, right? So if you compare the performance of this with the conventional parabolic reflector, which is shown in this particular figure, so this is the electric field distribution plot shown at 8 gigahertz for the flat reflector and the conventional parabolic reflector. So you will see that you have kept the plane wave incidence for similar focal length, okay, and the performance is very identical. So what you can see that the flat reflector can effectively transform spherical waves into plane waves, achieving highly directive radiation as it is supposed to work for the parabolic antennas, right. So these are basically the electric field ones that is showing you the wavefronts, right. Next we look into the next design, which is a flat lens antenna. So typically you will see convex lens is very common in antenna system. They can convert spherical waves coming from a point source or a feed into plane waves on the opposite side, okay, or you can see that cylindrical waves which are coming from a line source in 2D that can be converted into plane waves on the opposite side for the transmitter module. Or you can also you use this kind of lenses for incoming plane waves to be focused at a point that will be in the receiver side, right. So the objective here would be to design a all dielectric flat lens for C band and X band using discrete coordinate transformation. So this particular figure shows the virtual space with distorted coordinates. So this is typically a convex lens made of dielectric with permittivity epsilon r equals 3 embedded in air, and this is the physical space with the Cartesian coordinate systems, right. So the principle discussed previously, like the transformation electromagnetics or discrete coordinate transformation, is also extended to this compressed flat lens design. So the flat lens aperture basically uses 14 by 2 conventional dielectric blocks, okay. Here different colors tell you the maps of these different blocks. So this one, the first one, is basically having 80 by 15 blocks, so it is much smoother, and this is like only 14 by 2 slots, so you can see the colors more discretely. Each color stands for different permittivity values. Okay. So, what is the point here is that even you can make a flat lens aperture using this kind of 14/2 conventional dielectric blocks. Okay. And the key point here is that it employs dielectric blocks, okay, instead of metamaterials that could have simultaneous dispersive permittivity and permeability. And the way to calculate the permittivity distribution is basically can be followed from what you have seen in the previous example, right. So, the permittivity distribution you can see over here that gives this kind of physical space, and this one will work as this convex lens. Now, you have to compare the performance of this flat lens antenna that you have just thought of designing. So, you can compare the field distribution under plane wave excitation for the two cases. So, here we again show the electric field distribution at 8 gigahertz for these two cases, okay, for plane wave excitation. Okay. So, these are using, so here you have the conventional convex lens, and here you have a 14/1 block low resolution flat lens, right. Then on the other side for C and D, okay, here basically the line source is located at the focal point, okay, to feed, and this is again the flat lens and this is the conventional lens, okay, and that is showing you how you are getting the same kind of waves out of these two lenses. So, you can also do the focal length measurement. You can measure it from the center of the lens to the max field amplitude point. Okay. So, if you do the measurement, you will see that for flat lens you are getting it at 130 mm, and for the convex lens you are getting at 131 mm. That means the both lenses are able to focus energy almost exactly at the same point despite having very different profile. Okay. So, these two cases are basically showing you the emerging plane waves on the output side, right, coming from the lens. So, what does it tell you? That this confirms that the flat lens basically performs almost comparably to the conventional lens, and these are much easier to fabricate. Now, let us move on to the last topic, which is metamaterials for stealth technology. So, one important aspect of stealth technology is the radar cross section. That is basically the primary measure of how detectable an object becomes to the radar. So, stealth technology basically aims toward reducing this RCS, that is radar cross section, through different approaches such as shape mimicking or applying some coating, and also you can have metamaterials. So, metamaterials, we have already seen that they have amazing capability to manipulate electromagnetic waves in different new ways because of their negative permittivity and negative permeability. Also, the one thing to remember that metamaterial behavior can be seen when the unit cell size is much smaller than the guided wavelength. So, when you talk about metamaterials in stealth technology, it is basically known as radar absorbing material or RAM, that is basically used for ships, aircrafts and tanks. Okay. So, electromagnetic stealth can be obtained using metamaterials where you can do RCS reduction. So, you can apply metamaterials that can absorb radar waves. So, you are basically making a metamaterial absorber over a over the frequency ranges in which radar works. Okay. Or you can actually use some kind of material that can deflect the waves away from the source. That is also possible. In that case, the radar will not receive your reflected beams. That can be achieved using gradient index metasurfaces, or you can also think of scattering calculation by some sort of cloaking for core shell kind of cloaking, where a destructive interference pattern can cancel out the scattering. So, again the radar receives very little signal. So here we'll show one particular example of composite left-right handed structure that combines negative and positive parameters for broadband behavior. Okay, so you can this can be built using split ring resonators and metal wires. So wires array can give you negative permittivity and split ring resonators can give you negative permeability, which you have already seen, right? So this can be used to absorb radar waves by tuning to the resonance and matching the impedance to the air, making sure that you will get minimal reflection of the radio waves coming from the radar. So metamaterial absorber for stealth typical application typically looks like this. Okay, here it is designed for operating frequency of 8 to 18 gigahertz. It is basically a ITO pattern on top of a glass substrate. Okay, the glass substrate has a thickness of 0.3 mm and dielectric constant of 4.6, loss tangent of 0.015. There is an air layer in between, which the thickness is D, that is 1.8 mm. So you can see the entire metamaterial structure is roughly around 2.4 mm. Okay, this is the top view of the structure. So when you repeat this periodically, this is what you get. Okay, you can see that the absorption is very high over this entire band, right? So that means whatever the radar waves will be coming towards this absorber, okay, it will get absorbed and very little will be reflected. So that is a big method of RCS reduction, and that is how you can use metamaterials for stealth technology. So with that, we conclude our lecture. We will discuss tunable metamaterials in our next lecture. If you have got any query regarding this topic, you can drop an email to this email address mentioning the course name and the lecture number in the subject line. Thank you.